in that space of image analysis for diagnosis of cancer. But this is, very different, of course, and we are all excited. In fact, all the invitations I was sending, there were many people saying, "Wow, this I want to listen to." So we are live streaming on YouTube as well. But then the lucky get onto Zoom and get to interact with you as well.
I mean, that's typical. I wanted to make something different, right? I don't want to be, I don't know, like everyone else.
Yes.
And these are things that interest me, right? This is things that are kind of my fundamental motivation why I am in AI. And although, in the daily job, I solve problems like everyone else, on the, I don't know, night job is thinking about this problems.
Brilliant. Yeah. And I think, a lot of people need to get exposed to research in biological intelligence too, right? Not too many people, know a lot about it. And
yeah,
so
maybe not in the AI community, but of course there is a whole
yeah.
discipline with people and so on. But then these people don't know so much about AI, so somebody has to bridge. It's good to bridge things, right?
Yeah, no, absolutely.
Actually, I'm describing that a little bit in a book. I'm writing a book.
Oh, wonderful. Okay.
Entitled Next Generation AI. So it has to do with human brain and mind and how to implement that in algorithms and the difference between the two and how to make the two kind of merge together.
Right.
And work together. So I have to also describe some history. So that's what I'm writing about.
Wow. So when are you planning to kind of have that published?
Well, I finished chapter 2 and I planned 23 chapters.
Oh, okay.
And if I get a chapter in a month, so far I was able to get a chapter per month.
Okay.
So do your math.
So we'll be waiting a while.
Exactly. Yeah. It's not so easy.
Yeah. No, I especially with the number of things that you're involved with, right? So.
Yeah, of course.
So tell us a little bit about the advanced Bitcoin technologies. What's happening there with this startup of yours?
So I mean that has to do with SafeDroid, which is here on the slide.
I see. Okay.
So advanced Bitcoin technology owns SafeDroid.
I see. Okay.
And the what's happening here is basically developing tools for saving and investing in cryptocurrencies. Right?
Okay.
So we have an app that you can use to save automatically every day some money in cryptocurrencies.
Okay.
And we have developed an AI solution. The most interesting part of all is that automatically decides the portfolio.
Okay.
So which percentage of which cryptocurrency you will have to. So the AI is monitoring the market in real time, seeing what's happening, deciding on returns, volatility, volatility of volatility, seeing how the market is behaving, making a guess how the market will resolve its dynamics, its disturbances, and based on these guesses makes the purchases for the cryptocurrencies for the
okay, that's interesting because actually we also have a project in that space. So we've also been working in there. And it'll be nice to compare notes sometime, maybe offline.
Compared ourselves to Bloomberg crypto index, and we beat them last year.
Really? Wow. Brilliant. Very interesting.
And so, yeah, it's not bad. Not bad.
Fantastic. Fantastic. And of course, robots go mental. I'm sure everybody wants to hear about that. So hopefully there's something on what Robots Go Mental is doing. It's such a great name.
Say a few words. Well, I mean, I could say now a few words if
Sure,
that's
sure.
okay.
Yeah, yeah. Maybe a couple of minutes and then we can start the talk.
So,
Yeah.
so it's sort of it's not commercial yet, unfortunately. It started as a sort of a research project, new technology that we call transfer learning on steroids. So better transfer learning.
Okay.
So basically, the idea is that whenever you have to learn, you wanna train deep learning models with as few data as possible. And one way of doing that, from the theory of machine learning, is that you have to have inductive biases. Right? So you build inductive biases into deep learning algorithms. That's the traditional stuff, right?
Right.
Like convolution is basically an inductive bias that helps dealing with images, right? But what if you can train a neural network to learn inductive biases from a set of related images and problems, right? So, and that's what we came up. We developed a technology that can actually look one data set, learn inductive biases, and then on a new data set related, can apply them and then learn quickly. And basically, as deep learning has to explore this multidimensional space stochastically, right? The inductive biases kind of narrow this space and says, okay, don't look there. That's not going to be useful. And look maybe more here, right?
Right.
So this is like a whole set of algorithms that can do that in an automatic, generalized way, and it's applicable to any deep learning algorithm. So now we are looking for applications for some ways to monetize that.
Super. Well, I guess it's time, so we should start. Danko, first of all, thank you so much for taking out the time to come and speak to us. It really, truly is very exciting to have you here. Like I was saying earlier, we don't typically have cognitive scientists who have worked so deeply in the AI space and had, impactful, startups also. I think this particular webinar stands out for the fact that you bring almost three worlds together, right? Deep theoretical, underpinnings of AI research, cognitive science, and also its application in industry. And like I said, there's lots of interest here, and we are streaming on YouTube, so there are many people listening there too. And we look forward to your talk. And of course, people have come here to listen to you rather than me, so I shall keep quiet and hand over to you. And we look forward to listening to all of your experience that you packed into this talk. Thank you.
All right. So hello, everybody. It's a pleasure to be here. So let me start with this slide here. That's a robot that we would all like to have at home. And it's sort of a robot that science fiction has promised to us, and maybe it's futurist as well, that soon we will have a robot. So a robot that can do errands, keep tidy our home, and do everything that's needed over there. But we don't have a robot like this yet. What we have is just this little guy, and doesn't match really to what we would like to have, because there's lots of things left undone at home, like tidy up rooms, ironing stuff, taking dogs for a walk, and so on, right? So let's look at this problem a little in more detail. So what's happening here? Why don't we have a robot like that? So here on the left side, you see a video of a robot that can do a backflip, right? So this company called Boston Dynamics has released this video along with many others. And it's impressive to see a robot doing backflip. But then on the other side, we have dishes, right, that need to be done. And it would be good to have robots that can do dishes. Now, the question is, why would the company decide to do a robot that does backflip and not create a robot that does dishes, right? So if you look from the market perspective, what is the market demand for robots that can do backflips? How many robots the market need? Maybe one or two, I don't know. But how many robots does a market need that can do dishes, like including, picking up your table, cleaning the table, bringing everything to kitchen, cleaning everything, and just sorting the dishes back in the cupboard? How many does the world need? I don't know, probably a billion could be solved, right? So if that's the situation on the market, why on earth did they not develop a robot that does dishes? And the answer is very simple. They don't know how to do it. It's too damn hard. It's too complicated. It's so much easier to create a robot that does backflips, and that's why they did it. And this brings us to a problem of paradox called Moravec's paradox. And that's the paradox says that some things that are easy for machines are difficult for humans. Things that are difficult for humans are easy for machines. Like backflips are easier than doing dishes for machines. For humans are hard backflips, but dishes are easier for humans than doing backflips. And this brings us to the next point, that biological brains and machines work differently. It's not the same thing. Whoever tells you that their AI works like human brain, just point them to my presentation, to the rest of my presentation, right? So this presentation is about 7 differences between the brain and the machine. So let's go one by one. Difference number 1, types of errors. We make different types of errors than machines do. And to illustrate that, please, I'll give you a task. Look at this clock. Watch the second hand and detect the moment when the second hand skips 1 second. So my point here is that if something happens on the right side of the screen, you necessarily have to move your attention, at least for a split second. And this drives away your attention from the watch. So it could happen that exactly at this moment, the second was skipped and you didn't notice it and you're not sure anymore. And that's called the vigilance errors. We humans make vigilance errors. And machines don't. Machines do not make vigilance errors. Machines make so-called stupidity errors. They're just less intelligent. They do reliably things, but not in a very smart way. This is quite well illustrated by this movie that's more than 100 years old now by Charlie Chaplin, where they invented a machine for feeding workers in a factory. And at the beginning, everything works quite fine. And then even machine helps cleaning the mouth after the meal. But then things go wrong. The machine starts doing things wrong and the machine doesn't know what it's doing. And the poor guy is there in a trouble. So we make different types of errors. Number 2, concepts. Let's talk about concepts. If you are going to train a deep learning network to recognize chair, what you will do, you will give it many examples of photographs of chairs. So here are 8 examples. You may need a million. I apologize for this police chase that's just going here outside of my office. So you need millions of examples of the chairs. So then you get an AI, a deep learning algorithm that can quite reliably distinguish chairs from, say, something else, like bottles of cars or something like that. Now, do they have an actual concept of a chair? And it's not. The answer is not. They don't have a concept of a chair in the sense we humans do, because. And you can test this differently. You give them very unusual shapes of chairs that are still chairs, but are unusual. They don't belong to the data set. And you ask them, can they recognize those as chairs? Like, I'll give you some examples. Like, here is an unusual chair. And this is an unusual chair. Here's one more. And there you go, a really weird one. I have more. That's a chair. That's also a chair. That's also a chair, and here's one, right? Made out of suitcases. Right? So in a machine learning algorithm would recognize the last one as suitcase, and maybe it would identify 2 suitcases, but it wouldn't ever see a chair over there. And for us, it's not a problem because we have something else. We have a very different representation of what is a chair. And to illustrate the concept of a chair, you want to look at this picture. It's not actually, the chair is not defined by its features at all, but by the function that it does to our body. It's something we can sit on and take a rest, right? So that's our concept of a chair. It doesn't have to have even any features. It's the function of our body. And there are also different types of chairs because they put our body in different positions, different type of resting, if you will. So you can almost see here different types of chairs underneath these people, although there is nothing. Right? So big difference, big difference in how we deal with things and how machines deal with things. Here's more weird chairs, just to make my point stronger and stronger and stronger. And then how do we use concepts? It's not only that we have concepts to recognize things, we use them. Right? So here's an example. Look at this kid. This kid is a human. So it's a concept machine. This kid can do concepts. So we give this kid a car, one single example of a car to play for 1 hour, 2 hours with the car, tries it, drives around, tries everything, hurts itself, and so on, everything that kids do. And after that, the kid has a concept of a chair. Now, we draw this to the kid. And the kid may not recognize this drawing as, the concept of a car. And car has a chair, so it's also, a chair is included. But look at this one. Here, kids have, here you draw this to the kid, and the kid may not immediately recognize this as a car if it doesn't have drawing experience. But what you can do is say, look, this is a car now. And the kid will immediately map this to the concept of a car. It will extend its concept of a car. That's something a machine cannot do like that. You cannot train your deep learning on 1,000,000 images of a car and then take this one image and select, look, that's a car too. And then the machine select, yeah, okay, it's an equivalent of having, having had this example in my initial training data set. No, it's not. You have to start all over, train it all over with bunch of such images and so on. Right? The kid does it immediately. We humans do it immediately. Right? And not only that, now we can use that. Now, imagine the kid has played also with a train, with a toy train. Now you draw this. And if this was a car, you ask the kid, what's that then? And the kid then has no problem in generalizing and saying, look, that's a train. If this was a car, this is a train. And look, you see how powerfully our minds work, just instantaneously applying the new extensions to our concepts and combining them. And that gets even better than that. Look at this. Now I can go back to this drawing and say, this is not a car anymore. Now it's a table with 2 chairs. And what happens in your mind? A switch. Boom! You switch it immediately. Now you see a table with 2 chairs, no problem. Look how flexible that is. And then I give you this image. Now, what's that? If this was a table with 2 chairs, what's that? You'd have no problem seeing here a restaurant or a classroom or whatever you pick to see. See the flexibility. That's the flexibility of human intelligence. That's what beats deep learning big time. Right? And that concepts makes us smarter and more intelligent. And we have all kinds of concepts. We build them our entire life. We have concept about self that has lots of components. It's already been very expanded. Like the kid has expanded the concept of a car. Here we have, throughout the entire life expanded the concept of a self, with combining with other concepts and so on. And we have a very important in our life is a concept of time. Because we organize the world, the understanding of the world, of the universe over time, how things have happened in a sequence. Also, our own profession, there is lots of concepts. People who do machine learning, deep learning, have a very rich set of concepts of machine learning. So their concept of machine learning is very rich. I'm sure that's the case for most of the audience in this talk. Yeah? So that's how we work, and that's not how machines work. Right? Even self-awareness, like the consciousness, is conceptual thing. It's about the concept of self and being able to be self-aware and reflect in a sense, like this cartoon here says, holy smoke, I'm standing here. Well, it's just activating a concept and applying it to yourself at that point of time and making some new conceptual inference at this moment. And that's what we do all the time. All right, let's go to the context. That's difference number 3, context. So we humans are contextual machines, and machines are contextless. They don't care about context at all. And for us, context is very important. Now, to illustrate that, exactly for the purpose of this talk, I asked Cortana first the question, what is the capital of Germany? And the Cortana correctly said Berlin. And then I made the following. I said, and of France? So context is the capital. Did Cortana understand it? No. She said, I pulled some images of France for you. But I didn't understand the basic elementary context, right? And of course, it's possible for the software engineers or machine learning AI engineers at Microsoft to add a context case example for this particular problem or for a few more problems. But it's not a solution because our brain works naturally with the context. And somehow context is tied up to concepts that we just taught. Context, concepts come together somehow. Now, when doing this research, I noticed one interesting thing about logos of assistants, of our intelligent assistant. This is the logo of Siri. This is the logo of Alexa. This is the logo of Cortana, which we have just seen. So what do you think that the logo of Google Assistant looks like? If these are circuits, what is the logo of Google Assistant? Like, there you go, lots of circuits. It's, everybody uses circuits as logo. Now, where does this come from? I asked myself, why? And where does this come from? And then I remember something about something that preceded all of them, an assistant that preceded all of them. And some of you may have remembered. If not, I'll just show you now. That's HAL 9000. It's a circuit as well from a famous movie, Odyssey in Space. And then we already talked about this guy, a moving circle. So circles are everywhere in AI. That's pretty cool. Okay, now let me make a point that random is perfectly fine for machines. Actually, we know that. If you ask Cortana or Alexa random questions, jump from topic to topic, just totally randomly, they don't care. They're not going to get frustrated. They're not going to get tired. They're not going to give up talking to you, give up trying to have a conversation with you. This is not the case with humans. Try to talk to your friend or to your boyfriend, girlfriend, spouse in random questions, random stuff. You'll have a fight. You'll lose your friends very quickly. So, but deep learning, not only that deep learning doesn't care about randomness, there are cases when deep learning likes random. It prefers random. Right? And this brings us to the difference number 4, which is learning, the different ways how we learn, how machines learn, how deep learning, and how humans learn, right? So to illustrate that, I have here a video that kind of illustrates to humans what is it like to be a deep learning network that is being trained. Right? So what I did, I took just a sequence of random images. I literally Googled random images, picked them up, and classify them in 2 groups, living, non-living. And then basically I made a movie, image, text, living, image, non-living. Now I will play this movie, but I have to warn you that due to internet connection and a big distance between Germany and India, it may not work exactly smooth. But let's play it anyway. Okay, so I hope you have seen at least mostly, got a feeling, right? So the point is that that's what deep learning needs to properly train. If you start grouping living, non-living, it the training will be sub-performing. It will not be as good. Right? For us humans, it's just tiring and it makes us sick, and we cannot learn anything from such things. So how do we learn? Well, we learn from context and combining context and concept. And how we do that? Through stories. We humans love stories. Stories are contexts that evolve over time such that they are conceptually related. Right? So now to make this point, I took the same random sequence of images. Now you will see all the images again. If you missed some, you will see them now again. But I made up a story about it. Just made up a story that makes sense to human. So here's the story. Once upon a time lived a dwarf named Pepito. Pepito had a dog, Barfi. One day they hit the road and tossed a coin to decide where to go, and decided to reach Antarctica. They didn't trust airplanes, so they traveled through Africa by train. When they reached South Africa, they waited for a boat. While waiting, they went for a dive. And they met Horatius, who took them to Antarctica on his back. Success. That's the last one. Right? So now, after having told you this, after having retold you, re-shown you the same sequence of random images, but with a story that makes kind of sense for you, you will remember it for a long time, maybe for the rest of your life. Maybe if you hear my talk 5 years from now and I start referring to similar things, you'll go, I remember that story, Danko. I've heard it. That's how we memorize. And it's not only that we need sequence of images. We could take one single image, and yet we have context and stories because we take time to understand the image. Right? So this is one very famous image in the history of art by Ilya Repin, who is a Russian painter from this in 1883. And the name of the picture is "They Did Not Expect Him." And if you take a moment and if you look at this image, you will slowly start understanding why they did not expect him and who was not expecting whom. Right? So what you do, you take one part of an image, then you understand this part. You take some information from there. Then you move to the next one, and then you use the first one as a context to the next one, and next one, and next one. And finally, you understand the entire scene. That's how we understand static scenes. We take time and we build a story kind of like sequence of percepts and steps of understanding of the image, right? And that's actually when in neuroscience we do often research with such things. So one does eye tracking to see where people are looking over time, and then you can see people are typically looking at the faces of the people, because in this particular image, faces show where the attention is directed, and then they tell us a lot about the interaction, social interaction, and emotional expressions about from these people, right? Which is essential to understand this. Okay, difference number 5: creating new concepts on the fly. We have already seen with our kid, with a car, that we can expand concepts. But how about coming up with a whole new crazy concept right there on spot in real time very quickly? And I'll try to do that for you. I will come up with a concept: banana riding a bicycle. That's kind of weird. It's new. It's probably useless. And now, how can I enforce this concept for you? First, I can draw an image and then take this whole image processing things that I was telling you about, and then you take advantage of it, and then you will enforce this concept, banana riding a bicycle. But then I can go even further with the story. And then I can tell you like a real emotional story about a poor village in Africa where people are having a hard time surviving, and they have to walk long distances every day just to survive, to meet the end meets. And one of the efforts they sell bananas, and to transfer these bananas transport these bananas to the market, they use bicycles on which they carry bananas, and their bananas are actually riding bicycles, and this is essential for their survival. Right? So I have just now created possibly useless new concept for you, right? In no time, in a couple of minutes, right? And with few examples, with few words. No, I didn't give you a million images like deep learning needs, and then does not really understand anything. It just memorizes some interpolations of these images. You actually understand, and you understood it, and you can apply. Okay. Difference number 6: working memory. Now that's paradoxical, right? Machines can memorize millions of data points in an instant, in a couple of milliseconds. They can just acquire that and reliably memorize that. And now if you ask humans to memorize information, they are like really bad. They're really, really bad. And I'll give you an example now, right now, an experiment where you have to memorize colors, where which color in the space is, right? So are you ready? Right? Can you tell what changed on the image? And let me just tell you the answer. Yes, there is a change, and red and yellow change places. Okay? And probably most people caught it. And the reason you caught it is that we know that our limit of working memory is about 4 things. It's not more. So if I put 5, 6 colors, you would have really hard time. And with 7, nobody would probably know what the hell happened. Now, why? That's a paradox, right? That's a paradox. Why would we remember only 4? We are so smart, so intelligent, and we can remember only 4 things. Well, the answer is that our minds are not designed to memorize. Our minds are designed to apply concepts in the context, to think, to be intelligent. And when we are in a task of working memory, to memorize few items, we don't have a memory machine. We use our thinking conceptual machine to memorize. We're using super intelligent machinery for a stupid task for which this machine wasn't designed. Right? So we can understand all the relationship between these colors, and we're trying to probe our memory, come up with all the deep stuff that AI cannot do, but we humans can do it. But the task is designed that's just stupid, and there's just memory. Now, to prove that, I'll give you another task. A very similar, almost identical task. Are you ready? Now, the question is, was this item presented among the first 4 or not? And most people, well, people who are not Chinese character writers will not be able to answer that. And people who do write and use and are well trained in writing Chinese characters, then for them that's very easy problem. Right? So basically the difference is on whether you have a concept for these characters or not. Right? If you have concepts for each of these 4 characters, no problem. You can deal with that very quickly. If you do not have concepts, then you are hopeless, right? That's the proof. That's our experimental proof that working memory is actually dealing with concepts. And the answer is yes, this one was shown. And I turned it 180 degrees upside down to make it a bit more difficult. Doesn't prevent Chinese people to notice that. Okay, and the last one. We have long-term goals and also even multiple goals. Right? So we don't just do a task like do this, like recognize image and so on. Whatever we do, we somehow in a background have a big picture, a big talk in the background. So we may have multiple goals at the same time. We may have a short-term goal, a relatively short-term goal, like get a graduation. A real short-term goal is like eat lunch. And then a little longer is education. Even longer is, build a house one day, and even much longer is, plan your retirement. Right? So we have motivation structure behind our intelligence that work, and the two work together in a smooth way, in more or less smooth way. Right? It's not without problems, but it works quite well for us. And we even have like very flexible, structured motivation that we can do for sports, for entertainment, and so on. And to illustrate that, here is an example of a sport you probably never heard of. It's called extreme ironing, and the competition is to do ironing at the worst or at the weirdest possible place. And here is one during windsurfing. And here's a few more great achievements of extreme irony. Right? So let's get to the conclusions. The brain and machines work in fundamentally different ways. Only we use concepts and context and storage. Machines don't do that. Machines, this means that machines are not anywhere close to reaching human intelligence, not with today's technology. We have to change things quite a bit, fundamentally different. We have to have something fundamentally different. And this means that for the foreseeable future, humans will have jobs. Machines will not take over. And one of these jobs is dishwashing, right? We have dishwashers, sure, but there is a human part to it. It has to be assisted by human intelligence, and this will not go away anytime soon, unfortunately. As in my last point is that human intelligence, biological intelligence is not only human, it's also animals. And all the animals that you see around are much smarter than machines because they use the same principle of concepts and context and working memory and so on like humans do. They're a little less evolved, a little less developed, but it's the same principle, right? And that's why they can do dishes as well. So I have here a video of a monkey doing dishes, just to illustrate that. So that's the end of my presentation. Thank you very much for your attention.
Thank you, Danko. That was amazing. I love the examples you used and also the concepts that you were bringing across. And it's very refreshing because in the world that we live in today, there is this whole marketing around AI, right? About how it's going to take away all our jobs and how it's getting better than humans. Having said that, I mean, there are certain jobs that are definitely at risk, right? Because they were never meant to be for humans in some ways, I would say. Repetitive tasks and so on that are going to disappear, right? But this whole concept of artificial general intelligence, what's your prediction? How far are we from that?
It's really hard to say. So I think we didn't solve the fundamental problems, right? Mm-hmm. So, and if we did not solve the fundamental problems, we cannot tell how far we are. Right? It's not like we are on a track. We are not. We are just somewhere there, and we should be somewhere else. And we don't know where we should be. We don't know how to get there. So it's really hard to predict. Maybe something clicks, and suddenly everything evolves very quickly. Maybe it takes another 1,000 years. Maybe, right. I don't know. It's really hard to tell. I can whatever number I give you, it's my hopes. It's my wishes, not.
Yeah.
So, I mean, the point is that we have to go step down and look fundamentals and look at the neuroscience, cognitive science, and so on as a hint on what happens.
Yeah, because I mean, if you look at, there's a lot of press these days about GPT-3 and its ability to create natural language, and there's a lot of fear mongering as a result. But actually, when we look at these methods, none of them are really understanding text, right, and concepts behind it, and so and I think somewhere natural language processing seems to be the most difficult task out of all these, or would you say there are others that are also equally difficult?
I mean, I think NLP has its reason why it's very difficult, and has also its reasons why it is easy in a way. Some things are easier, some are more difficult. So the the reason why it's easier, the part that is easy, is that it uses symbolic inputs, right? So it just takes less memory, less computational power to deal with those than with images and movies and 3D space and so on. So that's the advantage. The disadvantage is that what's behind is extremely complex. It's human thought. It's
Right.
human ideas. And you will never, it's really hard to penetrate into them and actually understand what the hell humans meant when they wrote this text. You could get all the statistics of probabilities that words come together in certain order, which word after the other word, but it's not understanding what the hell they wanted to say, right? So that's the hard part. Now, the others, like, let's say, image processing, has a much harder part on the side of amount of data, because you have images, movies, right? But the problem may, in some cases, may be simpler, right? Because you are dealing with some world phenomenon that's not necessarily human mind. So self-driving car may be less complexity there in driving a car than in understanding Shakespeare, right? Now, imagine GPT, you know, GPT-3 was fed with all the text they could come up with pretty much, right? Now, imagine you do, I don't know, how do I call it, visual GPT 37, and you take all the images in the world, all the movies in the YouTube and everywhere, everything. Just how much resources you would need for training and all that, this would explode to the moon, I don't know. So, you know, so what would you get out of that? Something useful, sure. Would it understand? Not really.
But I mean, if you look at image analysis right now, right? I mean, they've been able to kind of identify objects within complex images and so on. But has there actually been work in even looking at the, you know, bringing ideas from NLP where they're looking at the context, right, of a word and what it appears with, and expanding what you can bring out from the image, right? So you might identify certain objects, not other concepts, and then you are getting into this whole process of saying, okay, well, you know, this object appears with all of these other objects, so it's probably related to these concepts. Is there a cross-pollination that you've seen of that?
Not that I know. Not that I know. And probably it's pretty hard when you look at the amount of data you would need, combinatorics.
Right.
Probably pretty hard, but it, in principle, could be one of the next steps that someone comes up with something.
So when we look at deep learning, it's obviously come out of the winter of AI and is enjoying a great summer right now. But from a cognitive scientist's perspective, do you see this model as being something that can deliver some of what you were talking about at a more conceptual level, or do you think there's going to be a change in direction, right? I mean, for people who've been in AI for a long time, we've seen lots of modeling techniques come and disappear. Do you think that this is in some way, I mean, it's still a statistical approach rather than a cognitive approach, right? Even though it's in some ways inspired by cognition.
Yeah, I think that two important things from my understanding. First, we will soon see that deep learning will start hitting the maximum that it can do, and this is due to computational demands. So if you see GPT-3, how much resources it needs, the jump from GPT-2 to GPT-3, the number of zeros they added. I don't know if they can do it once again. I don't know if there's enough resources on the planet Earth to do it once again, right?
Right.
Or maybe once, but not twice, right? Because it's just exploding. It's hugely exploding. It's like much, much faster than Moore's law, right? So they did, GPT-2 to GPT-3 less than a year. And they increased by the factor of, I think, 20, the resource demands, right? And in a year, you have 1.5 increase in resources according to Moore's law, right? So it's gonna hit the wall, the ceiling, soon. That's one thing. But then when you look to the cognitive science and the neuroscience, that's interesting situation, because it's not like cognitive scientists have the theory and figure it all out. No, we didn't. it's not like neuroscientists know how the brain works and it's just a question of explaining it to AI community. No, it's not the case. Actually, we're lost. We have a lot of phenomena discovered, lots of things, rules established, but the big picture, how it works, we don't know. We don't have. So it's important to understand that the AI, how we do it today, deep learning, that there is a good set of brain theories that are very similar to that. And it's okay, that's how the brain may be working. And then nobody can in the community come and prove them wrong because nobody knows the right answer, right? So there's this option, there's another option, third option, fourth option, and we know that all of them are wrong. So we are playing with them because we don't have anything better. And this means that, you know, this answer is also dependent on who you ask. Like some people in the community will be, you know, on one side, the other people will be on the other side, and so on. So there's lots of, you know, opinions, but nobody knows.
Mm-hmm.
So I have my own opinion, and that's what I'm writing a book about. But it, you know, I believe it's right, but you know, I have to admit, that I'm aware that it's just my opinion.
Sure. Karthikeyan, you've got a question. So the question, Danko, is there a possibility in future to make machines think? And the think is in inverted commas. So what is your view on that?
Could you repeat the think? I didn't acoustically hear it.
So is there a possibility in future to make machines think?
Yeah, I think it is. I don't know how, I mean, basically our brain is a machine. It's a physical device. It's nothing, you know, non-physical in there. And with some insights on how it works and how these principles are done, we should be able to make machines think in a way similar to human, but it will never be identical. And for the reason that we are not only using our brain to think, but we are also using our body. The entire body, the entire biological body thinks. It's not just the brain. The brain takes a heavy part, but it's the rest of the body as well. Like, think about the expression of a gut feeling. Gut feeling is not just an expression. It's a rule. It's a true thing. There's some 600 million neurons in the gut. There's some 80 million neurons in the heart, right? And you know, the having heart response, your pulse higher and lower is part of how we make a decision, right? If this increases the rate of my heartbeat, I feel differently about it, and I may make a different decision about it, right? Think about goosebumps. You know, when something gives you a goosebump, the skin thinks and contributes its part to the opinion, to the overall opinion, right? And when something gives you a goosebump, you take this in account to make a decision, right? Oh, I'll take, you know, you may go for it because it's exciting, or you may run away because the goosebump scares you, whatever you interpret it, but it's a part of the decision. So machines will never be able to make the same human type of decisions unless they have the identical biological body as we do, in which point they're not machines anymore, they're just us. Right? So there's always going to be some differences. Right?
That's interesting. I mean, I always thought of goosebumps as being a reaction of the brain, you know, transmitting to us, right, or our skin, a reaction rather than the other way around. Are you suggesting that there is actually evidence it's other way around?
I mean, you know, it's a partial reaction, but then it gets accumulated, but then, you know, it gets some, this is not caricature. Think of a skin as accumulating all the inputs and then making a threshold sigmoid function threshold decision and raising goosebumps. Then you have a sensory information coming into the brain, right? So it's a part of it.
It's a collective okay.
It's a part of the whole process, right?
Yeah.
And it's context dependent, and it's, you know, part of the concept of something, right? The concept of, I don't know, skydiving. It's a goosebumps is a part of it, right? So it's in parallel. It's the whole thing in parallel going on.
Interesting. Abhishek, you wanted to ask a question?
Yes. Am I audible?
Yes, you are.
So I was reading I was going through a lecture by a doctor who was sharing information about how our brain takes decisions. So even if we see some people, some tribes who are untouched by the modern developments, so even they know there are some things that rewards them and something that penalizes them. That's why they are able to live. Like whenever they eat food, their brain rewards them with certain hormones, certain chemicals that makes them feel good. And whenever they try to jump off something or maybe do something that they're not supposed to do, they get bitten off or some impulses that abstains them from doing that. So even like some idea of reinforcement learning maybe that is naturally built into us. So that's why like even animals know basic things like they need food, they need to reproduce, and different things that helps them survive. So that's some mystery how our brain was like actually has this thing inbuilt that some things are rewarding, and actually the rewarding things help us live longer and continue our species.
Okay. So was there a question there also, Abhishek, or was that just
No,
comment?
it was just about the idea, like the how we were discussing how we behave, we take decisions, and how machines are built. So maybe we need to think differently if we want to make them think. So we need to study our brains more, how they actually take decisions and how they encourage some activities.
Right.
Yeah, I agree. I agree. I had 7 differences, but this is not exhaustive. There are many more, and you just mentioned a very important one, right?
Right.
So there are many more differences.
There are some questions coming in from the YouTube listeners. So one is, can you tell any advantage of not having context in machines?
Yes, of course. There must be there must be always an advantage of anything being different, because we have in machine learning we have this no free lunch theorem, which basically means that if you have made something better here, you're going to get worse here. So there's always some trade-off. So I think the advantage of not having context is that you can quickly switch between different topics. Right? So imagine that you find yourself in a situation where you have to, for 1 second or a couple of seconds, be in a classroom and answer a question of a student. The next second you jump into your code and you have to write something. The next 5 seconds you are in a shop and you're buying, and then you jump around. Not being a contextual device helps a lot, because contextual device relies on context, and it's just making more difficult to switch this if the world is not, it's not working according to your design, to your architecture. So that's
sorry, go on.
No, that's the basic advantage would be
right.
that situation.
And then I think the same listener has gone on to ask, and what about emotions? Will it be good or bad for machines having emotions?
Well, I think of emotion as a necessary thing for our architecture to work. The architecture of how we are built. We cannot work without emotions, because think of it as like a huge democracy in our brain. You have like whatever 80 billion opinions, and everyone pushing in one direction, the other direction. Sometimes they may all agree, but most of times they don't agree. Some, when you watch a visual scene, you have so many different components, and each component is basically attracting attention to itself. So which one you are going to look? Your eyes may jump around. But in real life, you have to pick one thing to do, and you have to ignore the rest and be focused and do it. And without having an emotion in such a complex system, an emotion like some sledgehammer that decides that's what we are doing now, and everybody else who is not aligned, shut up, you can't do it. And the way how we work we as a conscious being, by having context, by having concept, by having all these things, we have to have, in addition, the emotions to actually drive us and decide where we are going out of so many different possibilities where we could be going.
So, I mean, the often cited example in the autonomous vehicles is the fact that, if a self-driving car is going down the road and it knows it's going to have an accident, should it swerve to kill the old man or a family of youngsters, right? And, what is right and wrong? And there, I mean, I guess,
that's an ethical question, right?
That's an ethical question rather than, yes.
Yeah, that's ethical. It could be ethics without emotions as programmed in. But I mean, regarding this example, I have a problem with this question, with this particular example, because it seems to me, as far as I know about traffic accidents, that such example only happens theoretically. It doesn't happen in practice ever.
Right.
So it's just sort of like philosophical entertainment, but not something that an engineer of self-driving cars has to worry about, because it just doesn't happen. I don't know if anyone could ever bring an example where this situation has happened.
Has actually happened, yeah.
Because think how unlikely it is. You have to have like these two targets possible in the same time. That's very unlikely, and then you have to be in all this situation, you have to be able to choose and to steer here and there. How likely it is, right?
Yeah.
For some, hypothetically, yes. In practice, it just doesn't.
Sure. But I mean, all of these things are very correlated, right? I mean, there's emotion, there's bias, there's contextual biases coming in, you said ethics coming in, and they're not independent of each other, right? I mean, what we define as ethical today is in some way affected by our emotions, our human kind of understanding of what is right and wrong, right?
Yeah, I agree. I agree with that. What is necessary that we build our values into the machines, and the positive ones and the good ones and the negative ones. We humans have as many negative ones. We somehow have to leave them out, like we do in our laws, right? In our legislative work. Most of the time we put in the good stuff. The laws are such to make things good, right?
Right.
99%. So we have to build our AI like we build our laws.
But then the application of the law,
bad stuff hide away.
But then the application of the law is still in the hands of the human who's biased, right? So that's why we get these impacts.
So AI would be like a law, but it's a law working on its own.
Right. Another question: how important or intertwined are behavioral sciences and data science?
Not a lot at all. I think the part where they overlap is statistics. So data scientists need to do often quite a bit of statistics, and behavioral scientists need to do statistics. Behavioral scientists have to build models about behavior. Data scientists have to build models about the data. So skills that you develop here are useful here, and vice versa. Mm-hmm. But that's like on the tool level. At the conceptual level, I don't see much.
But I guess, I mean, if we think about it a little maybe broader in terms of how important is behavioral science to really building true AI in the future, taking into account how we as communities create certain rules and behaviors that are acceptable, not acceptable. Does that really have to play into our development of artificial intelligence too, or not so?
Our AI will at the end have to reflect somehow social norms and the rules, and there will be some process of adjusting it, and there will be some early version that we will realize, okay, that's not what we want. We have to change it. There will be some struggle, fight cultural differences. Indian AI will be different from German in some ways.
Right. So related to one of the comments that you had made about deep learning and the resources that it requires, and is it going to hit a wall? Again, an obvious question coming in is, what about quantum computing, right? And, that could maybe free up and allow it to scale further.
Yeah, maybe, but I mean, I think it's important to understand very well what quantum computing can bring and what it cannot bring. It's not like an absolutely powerful machine once it works. It's the thing about quantum computing is that quantum computing does very powerful, very limited set of type of computations. Right? It's like, for me, that's how I explain it to myself. It's like having a trick, some natural physical trick to do your computation. Like, here's an example. You wanna count how many beans of rice are in a big sack or something. So you don't want to count all of them. You count in a small cup, and then you count how many cups are in then you just grab cups out of sack. So you use a trick of physical law that, space cannot compress under the pressure of rice, blah, 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 to make a trick to do this calculation. Now you are like, you can calculate in this way, you could calculate billions of rice beans in very simple, easy way. Like, it's like quantum computing. It's physical computing, basically. Both are physical computing. They are not Turing machines. Now, the cool thing about Turing machine is that can do any algorithm we humans can imagine. But these physical machines can do only something specific. Be it, the rice counting, be it the quantum computer, right? Now, the question is, are you able to turn your problem into this physical computing machine? If you can, then yes, you're not going to get great advantage. But it's not unlimited inflexibility like a PC computer. Computer is much more flexible. It always will be.
Mm-hmm. Thank you. Karthikeyan, do you want to ask your question by unmuting?
Can you hear me?
Yes, go on.
So that was a wonderful talk. So I just have a question based on neuroscience. So like we have this neurons, so they perform the same function, like they perform like this transmission of electricity through neurotransmitters, but all these neurons perform the same function. But how we could have this variety of functions, like we have this concept of memory, we have this concept of learning, but how could all these functions be done with just this simple concept?
Just a simple concept. You mean a simple neuron?
Not a simple neuron, like our neurons can transmit signals, right? So it transmits signals through neurotransmitters. That's how the neurons communicate. So it's just this concept alone is used for learning and memory, as well as other cognitive thinking as well. Like how is it possible? And how does our brain compartmentalize these functions?
So I hope I understand your question properly. But see, a neuron, yes, it's correct. It receives inputs from neurotransmitters, then it sums up those inputs and then produces some output. Now, neuron has inside the entire genome. It's a cell has a nucleus, it has a genome. This genome is making changes to the neuron in real time, continuously. Right? And every time you have lots of inputs, if you bombard your neuron with inputs, what you will have in a minute is something that's called immediate gene expression. So you have a high level of gene expression, and lots of new proteins will be created. And these proteins will travel to neuron and will build on the membrane, will insert themselves on the membrane of a neuron, and they will make changes to the neuron. Now, at that moment, the neuron is now a different neuron than it was before. Right? Now, genome has the knowledge on what to do, when, and it has, it has an entire evolution behind that, some 4 billion years since the start of life. So it has a lot of knowledge on what to do. We don't know what's going on and when is it and what are the rules. We don't know those. But what we know is that they are constantly active and changing. That's where learning is. And it's not only the synaptic learning. In deep learning, the only thing that you change is synapse and a bias. And a few other things, but it's the basics, like the synapse and a bias. A neuron, a biological neuron, changes a whole lot. a whole lot more. Like it can grow new connections. It can be big. It can become smaller. The entire space of neuron where there are no synapses is still covered by ion channels. These channels are proteins that are being generated. They come and go, and one type comes, the other type goes. It's a much, much richer thing. If you look at the activity of a biological neuron and a computer simulated deep learning neuron, they're completely different. They also behave differently. A deep learning neuron gets input, gets output. If it doesn't get any input, it's just quiet. Biological neuron is alive. It's literally alive, right? It's like a, like a little animal, if you want, right? It's sometimes firing on its own. It's checking out what's going on. It's receiving input. It's responding. It sometimes shuts up. Sometimes gets active. Does things all the time. It's a little live organism that we poorly understand. We poorly understand. We have simplified that to this description that you just mentioned, but that's a very oversimplification. It's a total oversimplification.
Thank you so much, sir.
Mohan, would you like to make your comment that, just unmute and make the comment you were making about, humans and their relationship to language and so on?
Yeah, thanks for that. And basically, I couldn't agree more than what Danko was saying, right? So it seems that right now, even what he's explaining, that basically in the AI and ML, we are still trying to bring the things on the physical level, right? And that's the whole difference between how the human brain on the overall, basically the neuron architecture works, right? That works very different. I mean, there is a dimension which is beyond the physical plane, right? Which we can perceive right now, right? And that's the whole what the talk Danko has delivered is pointing to. So that's basically the precisely what I was just looking to explain. So probably we need to think in from the AML point of view down the line that how we can basically bring that dimension which is beyond the physical context right now into the physical context and use it into the further research into the AI and ML space for the benefit of all.
Right. Thanks, Mohan. So Danko, the idea of whatever we are allowing AI to learn today is provided, fed to the AI by us, right? So in some ways, we are limited in how we can express our own knowledge by the language we use to interact with each other. And there is a lot of subliminal, like you were saying, the concepts that we can't describe ourselves very clearly. And so this idea of self-awareness, which Mohan has brought up, is how do we build self-awareness within artificial intelligence? Do we even have a model of self-awareness and an understanding of it?
No, so far, not that I know. Not that I know that someone has built a machine and has convincingly demonstrated that the machine is self-aware. Didn't happen yet.
Right.
But maybe I mean my understanding of this problem, which is I agree, it's exactly the problem that is. My metaphor is like explaining how a cell phone works. Like, so that's my cell phone. Now you can have two explanations. One is that I call grandmother explanation. You could look at it and you say, it works like this. You press the button, you swipe your finger, and then you get messages or whatever, or images. That's one explanation how it works. The other explanation is engineering with microchips and bits and bytes and electronic elements and so on. Right? Now, when we look at the mind, the human mind, when we observe our consciousness, our behavior, we're looking at this superficial, what's happening as a result. Right? Now, when we do neuroscience, we are looking in the electronics of it, but we don't have the textbook on how electronics transfers to the. And we are trying to figure it out. We don't know yet. Nobody has figured it out. Right? So when we are doing AI, we are doing exclusively, almost exclusively, we are doing the observation from the top. Right? So we are thinking like, how would I address this problem? oh, that's how my thoughts work. So let me try to build this same sequence in the machine somehow. That's 99% of AI effort, of AI engineering.
Great, thank you, Danko. And one last question. We are coming to a close here. Taranjeet, do you want to unmute and ask your question?
Yeah, thank you. So my question is regarding bullying. I have been reading a lot in this context from Jonathan Haidt and a couple of other researchers that, to create tough individuals, we need to provide them with a situation where, they are in stress. And typically in the universities, in the colleges, we are getting to a place where they have, a no bullying policy or a no ragging policy kind of thing. And that kinds of prevent the interaction between, the seniors or juniors because they are afraid of talking to each other. So I was thinking of a way that how we can regulate this process in such a way that there's a healthy way of interaction between seniors and juniors, so that there is certain amount of stress in professions, in colleges, and so that there is a character development of an individual. So regarding this, do you think there is a way where we can use data science or AI to create something that monitors or create processes, the health of an individual or the mental fortitude of an individual, to say that, hey, this person is in too much stress, or this person is, the bullying that's happening is not happening in a healthy way. So if I was to think of this problem as a data scientist, how would I do this?
Oh, I never thought about that. I have to admit, I never had this sort of thoughts. Probably one could do something, probably develop something in some direction, but it's always, you always have this, whatever application you do, you always have this trade-off between practicality, costs, and the actual result, the quality of the result, right? So, you could produce some result with extreme costs that nobody can pay for, like this. So it's in practice, it's hard to balance these things, right? It's not just the engineering part, it's also the economical part, human part, organizational part, culture. You have to put this all together to find a solution. And I've never tried this, work out this problem that you're talking about. I agree, it's important, it's great, it's useful, it could be useful in many ways. It would help people develop better, but I don't know. I don't have an answer.
Great.
Okay.
Thank you, Taranjeet, and thank you, Danko. This has been an amazing interaction. I think everybody's really enjoyed listening first to the talk that you gave, and also thank you for entertaining so many questions. I think it's been a perfect mix of hearing from you and being able to get our questions answered. So again, thank you so much for taking the time out to come and talk to us. And I hope that we'll be able to entice you to come back and talk to us about other topics too, on which you have deep expertise. And thank you again.
Yeah, thank you guys for having me. It was my pleasure. I enjoyed it. The questions were great. I love it.
Great, lovely. Thank you. Thanks again, Danko. Bye-bye.
Okay, bye. Bye-bye.
Thank you, so. Bye.